was really interesting that the previous talk from Telia was about data privacy, and we'll continue on that note right now, talking about one specific technology. So my goal is really to give an introduction to federated machine learning. And my name is Daniel. I come from a company called Scaleout. Reason why we show Uppsala University, so 3 of our founders are active researchers at Uppsala University with research teams there, but Scaleout itself is based in both Uppsala and Stockholm now, and we work with different kinds of customers, both in Sweden and in Europe. What we do really is 2 things. So one thing is helping early stage organizations doing their first AI projects, and we also help organizations that are scaling out their AI efforts, and we help them to solve bottlenecks in their AI or machine learning pipelines. But now we're going to talk about federated machine learning, which is the other major thing that we're doing. So we're building a platform for FedML. Now, you all know this, but this is an important context, I think, where we're starting. Going back to data. Data is the most valuable resource we have right now. That's how we create most value. And also, data by itself, when it's unstructured, it's a mess. And really, it's very hard to extract any value. And the predominant way to extract value out of data is going towards AI and machine learning. Now, maybe we're not really there yet, but that's where we'll be very, very soon. This approach and where we are right now by just randomly adopting or applying machine learning has some fundamental challenges. So the first and biggest one is around data isolation, that you cannot use all the data that you have. If you look at, there are a couple of parts to that. One is that you often have very sensitive or confidential information that you don't want to share with someone else, or you don't want to send it, or you don't want to move it. There are also many different legal aspects to this and challenges. So, for instance, HIPAA regulations, GDPR, other healthcare data, and there are loads of other also regulated data that you cannot do as you like with. And you also have a cost associated with moving data. So much IoT data, sensor data out on the edges is hard and expensive to move, especially related to the value of the data, related to how much data it is. The other aspect is around security, which now is becoming more and more as the value of data increases. You have to mine data security more. And the more you move, the more data you disclose, and the more data you share, and the more data you centralize. The risk of that data set increases very, very quickly. And this data is actively being targeted by hackers and other governments. And the last aspect that we were talking about earlier now is data privacy also. Maybe you don't want to pool too much data, because that becomes a very, very significant risk in itself. So what we are doing now, that we are looking at these aspects at Scaleout, and we want to solve this data sharing problem. We want to see and develop ways to build intelligence from distributed data at big scale. And we want to do that by preserving data privacy and security. So let's look at traditional conventional machine learning. You typically have your data, it's separated into different data stores. You pool this data together, you apply your machine learning algorithm, you create a model, and then you use this model. Now, again, this is something that is not possible all the time, and this is also something is being more and more aware that you cannot follow this traditional approach because of the regulated data, because of the sensitivity of data, and the risk of pooling data, and many times the cost of pooling data as well. So if this is a problem today, now we're moving rapidly into another situation where we're generating much more sensitive data. So rapidly digitalizing healthcare system, we have autonomous vehicles, we have factories going towards Industry 4.0, like generating vast amounts of data, in predictive maintenance, smart homes, personal robots that are very close to us. So we have to build infrastructure now to be able to monitor this data and use this data. And we need to build it ground up, caring for data privacy. So let's just 2 examples that I'll look a little bit more in detail. So one thing is around healthcare now, which is one of the first real big industries that are facing this problem. So in healthcare, we do create a lot of data. So it's data rich, but it's information poor because it's very, very hard to utilize all the data that exists. It's very hard to also find interoperability between data. It's very costly to move data, and it's very, very complex processes many times to collaborate also around data. So that's the situation that exists where we're like highlighting 2 different cases. So with all these variables in home monitoring that we have, but we really cannot combine this data with data being created in hospitals, like in different doctors or different healthcare centers. Another very, very common problem that many companies and enterprises face today is also in the wake of either very hard, expensive, and sometimes failed projects to create data warehouses and data lakes. So you have gone through a period of trying to harmonize and pool data internally, which in many cases have proven to be very, very hard. It's proven to be very, very costly, and these projects also have in many times either failed or at least been very postponed. So now you face a situation where it's how do you move forward? So do you continue to push these projects and try to get them finished, or will you try to start to create alternative ways to utilize the data and extract value from it, but without finishing the data lakes and the data warehouse projects? So, federated machine learning then. So the basic idea about federated machine learning is how can you create a machine learning model so where instead of you have the conventional approach where you pool the data first and then you train your models. Now you take your algorithm, you take the algorithm out to the data sets, you train smaller machine learning models, and then you have a way to aggregate these models together and build a combined model. So this is typically done by having a system that iterates over this system many times. So you have a model, it goes out to these the nodes, you create a small model on a data set. It could be like basically any kind of machine learning model or algorithm. You share this model with a central aggregator, but in doing so, you don't disclose data. You disclose parameters from your model, and depending on the model, there is a different amount of information being disclosed. And then you aggregate this model. You typically send out the model, once again, update these local nodes, and then you do this many times over. So then what's the benefit of doing it this way? So in this picture, you can think about the x-axis as basically the size of the data set, and that is decreasing. So as your data sets decrease, it's very hard to create one model that will capture all the value of that, the potential value of that data set. So this is a toy example, but coming up from a publication we're doing, just to showcase what happens now that if you're in a situation where data is distributed, you cannot train a machine learning model on any one of these data sets and get to the full value of the potential value of this machine learning model. But if you can use all the different data sets and combine the information, you're able to create a federated model that will have a performance that does not deteriorate then as the data sets increase. So it's a way to capture how this value from distributed data sets, where maybe not all data sets contain all the information that is needed. So that's a key benefit now. But we also have some follow-on benefits. So for instance, that data security and privacy increase when you never move data. You just move information about these models. You can also achieve very powerful data network effects in some industries where you cannot transfer data. And you can reduce transfer costs also, because data can be very large, and these models typically tend to be very small. So this is, I dropped out, but this is a way from the UN Handbook of Data Privacy, how they look at data privacy. You have 3 different main domains. You have input privacy, we have output privacy, and then we have policy enforcement on top of this. And if we look at federated machine learning, how that relates to data privacy now. So the natural starting point is the input privacy. By using federated machine learning, you don't move data. So you increase this the chance of disclosing data to a very large extent. Now, on the other side, you cannot learn anything about the data by looking at the models that are the result. This is also part of the output privacy part. What can you learn of the models, or what can you learn about the data in the models? And by doing federated machine learning, usually, depending on the models or the algorithms you choose, this is something that you can adjust and be in control of. And what we are working on the Scaleout is actually on the top part, the policy enforcement part, which is typically, it can be a technical thing and/or it can be related to us humans. But we are building our systems to handle this in automated ways that everyone can trust. So here are some different terms. ZK proofs, HEMPC. So that just stands for different methods to further enhance data privacy, and how you can apply this also in this federated machine learning setting. So HE stands for Homomorphic Encryption, for instance. So you can combine different methods to increase data privacy together. And work in this area is something that we work very closely with these research teams from Uppsala University. And this is beyond state of the art, so many of these things are not things that are in production anywhere in the world yet. But it's important work, and people are working on this. And we have different ways. So as it has been traditionally, for instance, differential privacy is what's used on our phones from Apple. They are using, that's the only way that they are enhancing data privacy with the things that we type in for URL prediction, for instance, in the Safari web browser. Otherwise, they are basically collecting all the data that we enter. Secure multi-party computation is something that is a bit important, and we'll get back to that. That is how you can perform computation at someone else where you don't really trust the environment, or how can you trust computations that are done, or processing that are done somewhere that is you don't have full control over. Now we started with the basic setting for federated machine learning. And so that exists today. There are naive implementations, and you can use that in some cases. But to make this really useful, we need to go further. And the current research development that's being done, I think, is from our side, it's in 3 different areas. So one is about scalability and machine learning performance. And this follows because if you previously would pool all the data in one place and you you have that in a cloud setting where you have basically infinite compute resources, then of course it can go pretty quickly to train your models. But now if you distribute this and you go and perform the training where the data is, how do you have access to the right compute power that you need? So this is work that has to be done on a algorithm level to, in many times, optimize the algorithms to do the training better in other settings. And then in the long run, like how do you develop these also algorithms so they are useful out in the edge case or fog computing case? The middle section here is about adversarial machine learning. So also, like if you are in different settings, which I will get to, because federated machine learning allows you to collaborate also with both internally in companies, but also between companies and even with competitors. But how can you trust that everyone in a setting like this is honest and is also willing to do what's best for the entire group, and they're not part of this in order to try to learn as much as possible, maybe from the other members' data and their contributions. So this is something that is important, and we're doing work on. The last part is around decentralized computation also. How can you trust computations that are being done with someone else, where you don't have full control? So I want to dig into the last question a little bit, so which is where we're doing most of the work internally with us right now. We have like 2 projects going on. One project is like thankfully supported by Vinnova, which is how really to add trust into these systems. So how, if you have an alliance like this, maybe now you're not only working with your own data, but you are collaborating between companies. You have to trust that the model that is being generated is secure. You have to maintain full data privacy, and you have to trust that this model is not misused by anyone in the group. So typically what you would do is that you would have a trusted third party. Like we assign someone, and that everyone can agree on that we trust this entity. But we want to create a system where you don't have to trust anyone, because you have a trusted base layer built from technology, basically. And in this case, we're using blockchains. So blockchains are a very, very good way, in some cases, to add trust to systems, because data you create can never be changed. So it works like a trusted ledger here. And that's the project that we have, like also good support from some of these big organizations here that are part of, like making sure that this is something that is really related to like practical use cases right now. The other like internal project that we're doing is how to form secure alliances also. So basically more of a front-end question. There's no video now that when it's a PDF, but this is it was supposed to be a video of the interface that we have. But it's just the way that you're, in order to be able to work more actively with these alliances and models, you need to have an easy way to interact with them also, and to set up governance, for instance. Okay, so now, like this is basically to finish off. So it's 10 minutes to go, and I wanted to talk more about some practical use cases of federated machine learning. So we have 2 main types, our settings today. Like I mentioned really early on, that healthcare data is an area where you have problems today. You have lots of data, but it's very, very hard to collaborate around this data. And we actually have 4 it's still early stage projects, but projects going on that is related to this. And the typical setting in healthcare is that you work in a setting where data is spread around, and you typically have a non-competitive setting. So everyone here is interested to generate a resulting model that is as good as possible. So in practice, this might be that you have one system provider that provides some kind of a system that is used in different hospitals. When you're using this system, you're generating data that could be used to train the system. The problem is that you cannot transfer data now from each hospital back and learn from this data. And this is like no-go today. So one example of one of the companies we're working with, the approach is usually to go to your biggest hospital or biggest user, and you use that to train a model, and then you hope that this is good enough so that you can create a system that is useful for everyone here. But what if you could instead use data that's being generated just from the usage of your products across all hospitals? So then you're back to this graph that I showed in the beginning. In these cases, when you're looking at X-ray images, which is a typical case here, like when you're doing machine learning on images, you typically need a really big data set in order to create something that is useful. But one hospital does not create enough data to make it possible to create a very well-functioning model with high accuracy. But this can be solved if you can use data from many different hospitals. Okay, so that's good. And this is a situation that is also very similar to many other types of companies. So you also might have, like within a company, you have either subsidiaries that you have different data sets residing in different subsidiaries. Everyone wants to collaborate, but for different reasons, it's not possible to work on these different data sets and transfer data sets between different subsidiary companies. And then could also be one way to do it. And what's nice about this setting is that you trust each other. So you don't need these other functions of you don't need to disintermediate the trust. You don't need to remove full trust from the system. What's most important here is that you don't share and disclose data. Now, if we go forward, so one of the really interesting, still early stage projects we're doing is with Eurocontrol that manages the air traffic space or airspace across Europe. And what they're doing is that they're trying to figure out ways for how to optimize probably everyone here has been standing on an airfield and you're told that your slot time just disappeared. Now you have to stand here and wait for next. And that's Eurocontrol. And what they are aiming to do is, instead of their current approach, which is just to try to predict how to minimize overall traffic flow and congestion across at certain airports, they want to give an option to airlines to actually build predictive models that include financial and operational data into what they're doing, so that when Eurocontrol chooses if this airplane or this airplane loses its slot time, they're going to choose it by choosing the plane that has the least amount of economic effect on that airline and the overall system. And this is a problem then that is really interesting, because here you have competitors in these really big industries, but they have an incentive to work together and to try to create a good model here as possible. But at the same time, they never would like to disclose any of their data to their competitors. So the follow-on system here is, okay, so now how can we then create systems where you both have trust, but the follow-on thing here is how to create incentive systems for everyone to participate as much as possible into building as good common model or collaborative model here as possible. And this is something that you can find in other industries as well. But the concept of collaborating with competitors is, I think, something that is a bit far ahead for most enterprises. And I would really like to hear some thoughts here from you guys, if that is also common or even possible in the industries that you are in. So with that, last thing. So there is, if you take a picture, there's a question or two. Yeah.